Aloha. My name is Dr. Thomas Peratt, and I am a research associate for Dr. Don Thomas at the Hawaii Institute of Geophysics and Planetology at the University of Hawaii. I'm here to discuss with you the Red Hill Dye Tracer study currently ongoing at the Red Hill Fuel Facility. The University of Hawaii's research objectives were to use modern tools and methods to develop a better understanding of the regional geology using geophysics, document groundwater flow rates and directions with the colloidal borescope, and to validate those findings through the execution of one or more dye tracer tests, as was presented by Dr. Thomas at the Fuel Tank Advisory Committee, FTEC number 13, last October. So why do we do dye tracer studies? Well, there is a variety of reasons. The most common is to better understand river dynamics for drinking water protection, as done here by the USGS on the Kansas River. Also to study groundwater migration and to identify areas of discharge, as was previously done by the University of Hawaii at a reclamation well in Lahaina. And to understand the application of liquids. Here you can see the U.S. Army Corps of Engineers doing a herbicide application study in Idaho. However, at Red Hill, we're most interested in the groundwater migration within fractured bedrock. An overview of a dye tracer study within fractured bedrock is as follows. First, a fluorescent dye is injected into a well. Samples are then tested with a fluorometer to determine the concentrations. In a single well test, you can only determine how quickly the plume dissipates. However, in a multiple well test, you can estimate both the arrival times of the fractured flow and the diffused plume. And in our case, used to evaluate the capture of an extraction system by looking at the total mass of dye recovered. Past dye tracer studies in Hawaii have included the Lahaina Wastewater Reclamation Tracer Study. UH injected 255 pounds of fluorescein dye in cooperation with the Department of Health, the EPA, and the U.S. Army engineers. A maximum concentration of 35 micrograms per liter, or 35 ppb, was detected offshore half a mile away. The seeps were very small and barely detectable to the visible eye. Here's an example of the dye seeping into the ocean 75 feet off the shore. So even with 255 pounds of dye being injected, only very small concentrations were ever observed offshore. There was also a groundwater tracer test at the fuel storage facility at the Wheeler Air Base. 12,000 gallons of diluted tracer was injected over 6 days. It was determined that a prolonged injection of dye over multiple days is preferred to a short, highly concentrated pulse of injection. The observed concentrations were very low, less than 10 micrograms per liter, or ppb. These results were then used to calibrate the groundwater transport model at the Wheeler Army Airfield Base. It would require a much larger mass, though, for detection at Red Hill Shaft due to the dilution. So what is a fluorometer? It is used to test the fluorescence of a liquid. A fluorescent substance will emit a low energy light when exposed to an external light source. Here, the most common example we're used to is a black light. However, with rhodamine, you can see here when it's excited, gives off this reddish color. When you turn off the external light, the water stops glowing. And these concentrations then can be easily estimated by the brightness using a fluorometer. Essentially, the sensor emits the light and detects the response at a specified wavelength. So what dyes are typically used for these tracer studies? Fluorescent dyes approved by the EPA and DOH are typically xanthine based. Xanthine, you can see the molecule on the right, can produce the two most common dye tracers, fluorescein and rhodamine. Past studies in Hawaii have used both the fluorescein, which is green, and the rhodamine in red due to the nitrogen. Rhodamine, though, can exist in a variety of different forms, with rhodamine B and rhodamine WT for water tracer being the most common and are only different in their polarity. So rhodamine B is much less water soluble than water tracer due to the fact it is nonpolar. Sulfur rhodamine B was the form used at the Lahaina study. You may have heard in the news recently about red dye number 3 causing cancer and being banned in foods. That's due to it containing iodine, which is known to cause thyroid cancer. The rhodamine used in tracer studies do not contain any iodine. So rhodamine WT will be used at Red Hill and has been approved by the US EPA and the Hawaii Department of Health and been used by decades for the USGS at very high concentrations. Here you can see a dye tracer study performed by the USGS at Stinks Canyon in 1983 with the dye seeping out into the river. Not to worry, the purpose of the dye tracer study at Red Hill is not to look at detections within the streams or rivers, but at Red Hill Shaft. We are not expecting any dye to be visible to the public. Again, here is another example of the USGS injecting large amounts of rhodamine WT into a river. However, recent toxicology studies found concentrations less than 910 micrograms per liter are safe to aquatic life. Rhodamine B, though, was found to pose a risk to aquatic life at lower concentrations, around 140 micrograms per liter, and was found to be sometimes 15 times more toxic than rhodamine WT. 50 pounds will be injected over 5 days with 5,000 gallons of drinking water from the Navy's Waiawa shaft. This is 1/5 of the mass used by the University of Hawaii at the Lahaina tracer study. Red Hill Shaft will also be pumping 24/7 at 4.2 million gallons per day to capture all the dye, which would result in a theoretical maximum concentration of 285 micrograms per liter. And here is the equation in which that is estimated by taking 10 pounds per day, which is roughly 4.54 kilograms, or over 4 billion micrograms, and divided by the number of liters of 4.2 million gallons, which results in the 285 micrograms per liter. Additionally, the dye will be filtered out by the granular activated carbon system prior to discharge to Lavawa Stream. In the unlikely event dye does discharge to the surface, it degrades in the sunlight with a 15-day half-life. So where will the dye be injected and monitored? The dye will be injected at RHMW08, approximately a quarter of a mile away from Red Hill Shaft. 6 transducers with rhodamine WT sensors will estimate dye concentrations of the water pumped from Red Hill Shaft every 10 minutes. Here is an example of that transducer and the sensor that it's equipped with to detect the rhodamine. Also within the injected well, RHMW08 every 15 minutes, and then at 4 additional monitoring wells every hour. 18 additional well locations will be equipped with passive samplers, which are essentially comprised of a charcoal to absorb the dye. Every 2 weeks, the mesh bag that holds the charcoal are replaced and sent for laboratory analysis. Wells in which a passive sampler cannot be deployed, such as West Bay wells or wells with an obstruction, will be analyzed with groundwater samples and a tabletop fluorometer. Again, all Red Hill Shaft's discharge to Law Stream will be checked post-GAC to ensure the dye has been removed. Here is a figure of those locations. Injection at RHMW8 will begin mid-February 2025 as seen by the red cross in the center of the figure. Readings from RHMW08 suggest that the plume will migrate at an angle of 235 degrees at approximately 50 feet per day from the collider borescope. Detection at Red Hill Shaft then is anticipated within a month, likely before March 2025. Monitoring will continue until the dye is no longer detectable within the spring of 2025. The expected extent of the rhodamine W-team plume with capture at Red Hill Shaft is shown in the purple oval. Preliminary results will be shared with the public after monitoring is complete in the summer of 2025 and presented at the fall FTAC. We will gain valuable insight into groundwater flow and provide data sets to inform current and future modeling efforts. Also check out the Red Hill Dye Tracer Study FAQ for additional answers to questions you may have. If you have any additional questions or concerns, contact me, Dr. Thomas Peratt, at tum@hawaii.edu. And finally, a special thanks to their Navy and their team for access and assistance throughout this study.